So we proceed with the second medalist for this year. So another Colonnetti Medal for 2023 was awarded to Dr. Franco Zunino, who is currently an independent scientist at ETH Zurich after being awarded his PhD at EPFL in Switzerland. His research is mainly aimed at further elucidating the mechanisms of hydration and sulfate balance of blended cements with the aim of developing innovative solutions for low carbon, high performance concrete. Dr. Zunino's studies have resulted in numerous publications in collaboration with the research groups in different countries. The high impact of his research results, testified by an impressive number of awards and prizes, has recently secured him a prestigious grant, thanks to which he will further pursue the route to ultra-green concrete by a combination of blended cements and optimized admixtures. Dr. Zunino is also active in science dissemination through instructional videos and seminars, including the Rock and Talk series, which we heard recently. He is also involved in a panel of experts from the United Nations Environmental Protection Agency. So congratulations to Dr. Zunino, who is welcome to come to the stage.
Thank you very much for the nice introduction. I would like to start my presentation by acknowledging my colleagues, former colleagues and former supervisors, well, many of them are here today joining us, and us watching Zaid in his presentation. Without them and without their contribution, none of this would be possible. So the point of my presentation and the things that I want to show today is a bit the work that we have done in the past at EPFL, now at ETH, and also the vision of this project called Ultra-Green Concrete, or how could be, in my opinion, a pathway for low-carbon concrete on a quick and easy-to-implement way on a worldwide scale. So I'm very glad that the presentation of Karen preceded mine, because she showed some of the figures that I'm going to use here, so I guess on some parts I will be able to go faster. But I think it's important to insist in the fact that we cannot lose the perspective. And concrete, when we talk about concrete, we are talking about the second most used substance after water. We use a lot of this stuff. And this is basically why the Portland cement that we need to make this concrete is accountable for about 7% of the industrial energy use and roughly 8% of the anthropogenic CO2. During the presentation, I will make a lot of these distinctions, so I know that you are all aware of this, but you will see why this will make sense down the line. Portland cement is this combination of clinker and gypsum, and concrete is a much more complicated mixture of stuff, where actually cement is the minority of the volume, and about 70% of the stuff is this skeleton of aggregates with different ratings in order to fill the space. But if we look at the CO2, it is very clear that most of it is coming from this clinker fraction. So even though we have a minority of the volume of the concrete made out of cement, most of the CO2 is coming from there. And it makes a lot of sense then that during the last 10, 15 years, our research efforts have been focused to reduce the clinker factor in cement, because this is where the CO2 is coming from. We cannot miss perspective, and I'm very glad that Karen introduced this plot before, though, that concrete is a very efficient material from an energetic and from a CO2 point of view, particularly compared with the spectrum of other construction materials that we have available. So concrete is a low-carbon material today, and it will remain dominant. And I think that I don't need to insist this further after the arguments given in the previous presentation. From a scientific point of view, for myself and for my students then, we are looking at a problem of optimizing a material that is already the optimum that we have. And this makes it, in my opinion, particularly challenging. So, given though concrete and cement-based materials will remain dominant, clinker replacements, what we call use SCMs to reduce the clinker factor, is recognized today as the most efficient way to reduce the embodied CO2 of cement. But the problem is that in the last 10 years, 10-15 years, and Karen already introduced this plot, we haven't made real progress on increasing our replacement level. And there is only 3 materials, limestone, fly ash, and slag, that we are using in quantity. And the reasons for this, you can think that they are diverse, but are mainly related with availability, as we will see in the next slide. The problem is that we are stuck in this range of 20 to 25% replacement, and on the other hand of the table, we have roadmaps for CO2 savings, like the one that GCCA is proposing, which is aiming to get an average clinker factor by 2050 of 0.52. So the question is how we are going to materialize that average clinker factor of 0.62 when a situation where we got stuck already at 25% replacement. So we have halfway to go. So the first argument for going then for limestone and calcine clays is definitely an availability one. So we haven't been able to increase our replacement level of clinker by supplementary cementitious material because we don't have enough stuff. If you compare the demand of cement today with the availability of other materials, you can see that there is no way to replace, let's say, 50%. And it's only calcine clay and limestone, these 2 materials, that can really change the situation because they are available in quantity and they're available, more importantly, in the places where we need cement and concrete production, which is in the emerging economies. A second argument that I would like to add to the availability one is a reactivity argument. Calcine clays are by far more reactive than the other SCMs that we have around, and I hope to convince you during my presentation that reactivity is not just a metric, it's also one of the keys that we have to save CO2 when we talk about low carbon cement and, more importantly, low carbon concrete. So very importantly in this pathway to low carbon concrete is LC3, and what we have achieved with LC3 is remarkable. So this is a project that has been led for the last 10 years by EPFL in Lausanne in Switzerland, and it's basically a blended cement, so we are still talking about Portland cement-based materials, which combines clinker, calcine clay, limestone on a 50% replacement ratio, basically allowing us to save between 30 and 40% CO2, and most importantly, achieving equivalent performance to Portland cement and enhanced durability, as Karen detailed. I'm very happy that in this presentation I can already confirm to you, this was not the case a few years ago, that this cement is already included in the European standard ENY 97 under the denomination CEN2C. So, while this is like the typical combination or recipe to make LC3 that we tend to show people, it's important to realize that LC3 is really a family of blended cements, and these proportions of limestone, calcine clay, and clinker can be adjusted in order to get the properties that we need for a particular application. So we are basically here in what we call LC3 50, 50 standing for this 50% clinker factor, but I see significant opportunities for going even further in the reduction of clinker content, and this avenue is basically enabled by the high reactivity of calcine clays. And I would like to show some results and some thoughts in this direction during the presentation. So the first question that I would like to share with you and invite to the discussion is that is really the 50% clinker factor the final frontier for LC3, or we can think that in some markets and in some applications we can develop materials with even lower amounts of clinker. And does it actually make sense to do that? So certainly, when we look at the CO2 saving potential of LC3, again quoting this number that we have repeatedly insisted during the presentation, between 30 and 40% savings, and we get, as you see there on the left, comparable strength compared to BC. And certainly, as we start decreasing further the amount of clinker, well, we don't get the same strength at BC anymore. The strength will start going down, and also the CO2 start also going down as well. So this is probably something that you were expecting. So what are the CO2 saving potentials from doing that? Well, if we go to something like 35% clinker, we can save between, let's say, 47 and 54% CO2. If we go to something like 25% clinker, we can save between 60 and 64% CO2. Refer to CEN1, refer to OPC, and assuming that we are replacing the clinker with a combination of calcine clay and limestone. But the strength is also going down. So then the question, does it really make sense to do this, is not obvious. And also, we haven't answered what are the challenges and the technical barriers to actually do that. Like, can we actually do it in a way that is reliable and it makes any sense? So, in terms of strength, I'm comparing here, I'm showing you results of LC350, and on the right side you have LC335, so we're already pushed quite below the 50% clinker barrier, and you can see that the strength is actually not so bad, but it's certainly not the same strength level that we get with OBC. And we need to understand why this is happening. On one hand, when we have blended cement, we have clinker hydration, which is kinetically faster than the reaction of SCMs. And we have the reaction of the mineral additions, in this case the calcium clay and the limestone, because remember that there is a synergetic reaction between them that is kinetically slower comparatively to the clinker. And what's happening is that as we decrease the amount of clinker and we increase the amount of SCMs, we are putting much more of the slow stuff and we are reducing the fast stuff. So then my development of strength is also getting retarded compared to BC. And this is key to keep in mind because in some way reducing the clinker further is an opposed concept or is driving me in a direction that is opposing the early strength development. And this is something that we need to look at from a scientific point of view in order to find a solution if we want to go in that direction due to the, interesting CO2 savings that we can get. So, does it make sense to do this? And I will reintroduce the slide that Karen already showed with a little bit more of detail. So, I'm originally from Chile. This is a country that is famous for its low clinker factor. It has today an average clinker factor of 67% in the bagged cement. This is not because the industry is particularly sustainably driven, it's basically because there is no limestone in the country and producing clinker has always been very expensive. So from a cost perspective, they have always been forced to introduce a large amount of SCMs in the cements that we use. And one of certainly the standards of the country are made around these pozzolanic cements that are available. And one of the strengths that we have, well, these are the two red bars that you see here in the plot. There is a high strength grade which has 80% of clinker factor, and there is a general use which is this pink little one here which has 65% clinker factor, and then we are replacing that with calcium clay. And we wanted to compare these with LC335 and LC325, so 35% clinker and 25% clinker. The lines that you see here, these horizontal lines, are the requirements of the standard for both grades of cement and 7 and 28 days. And we can see that we can meet the requirement of high strength with LC335 and for general use with LC325. So basically with low clinker LC3s, we can meet exactly the same strength requirements that are in the standard, but saving about 40 to 45% more clinker than if we do it with natural pozzolans. And the difference between doing it with natural pozzolans or with a combination of calcium clay and limestone is reactivity. So this is why reactivity matters. It's not the same using inert materials or fully reactive materials than using very reactive combinations like limestone and calcium clays, because this is what opens the gate to further reductions of clinker content, retaining performance. Why it is working so well then? Why this such difference that even with 40% less clinker content, we are getting the same performance than a pozzolanic cement that has much more clinker in it? And the magic is really the synergetic reaction between metakaolin and limestone that leads to precipitation of carboaluminates, as Karen introduced in her presentation. And we can see here on the plot that where we are comparing LC335, 25, and LC315, actually we went quite crazy with the reduction in clinker content, to an LC350, which is the classical one, that as we reduce the amount of clinker, you can see that the amount of carboaluminate is becoming limited and chopping off, plateauing earlier and earlier. And this is because we are running out of Portland. We are taking more clinker out of the system. We are running out of Portland than earlier, and we cannot sustain the reaction of metakaolin longer. So then, an idea could be what happens if we add a small amount of Portland in order to boost back the reaction of metakaolin in this low clinker system, and this is basically the blue line that you see here, where you see that we can completely increase the amount of reaction that we have, which is also reflected in the evolution of the degree of reaction of metakaolin in these systems. So basically, the addition of Portlandite in LC350 doesn't make any difference because this system is not limited by Portlandite availability. There is plenty of Portlandite to make it react. But in LC325 and LC315, we are limited by this and by pushing using this admixture. And this will be a keyword during the rest of the presentation. By using this accelerator admixture to boost the reaction, we can actually recover a lot of this reactivity of metakaolin. In terms of microstructure, this basically means that we have all of this Ni and monocarbon, which we know now precipitates occupying large pores left behind by clinker hydration, reducing porosity very effectively, very quickly. This is a reaction that has its peak between 2 and 3 days of hydration, and definitely contributing to this gap difference between a system with 25% clinker and a system with 65% clinker, depending on the SCM that we're using. On the second part of my presentation, I would like to invite you to follow me in the concept leading to the project that I'm leading now at ETH, which is called Altering Concrete, which main idea, if I have to summarize the concept of the project in one sentence, is to move the focus, which is now in cement, back to the construction material that is concrete. And I would like to start this section by this very kind of challenging title there. But I hope that you follow the idea that I'm not trying to point the finger to anything, but actually put everything into their measure. So concrete is a building material and cement is not. We don't build infrastructure or houses out of cement. And at the end of the day, what really matters if we are concerned about CO2 footprint is the amount of CO2 per unit volume of construction materials that we're putting in the field. And this certainly depends on the clinker factor. As we saw in the beginning, 96% of the CO2 is coming from that stuff that we call clinker. But also, when we start thinking about concrete, things like the binder content, how much cement per cubic meter I'm using, becomes particularly critical, and how much admixtures I'm using in order to control the properties of that concrete also become critical. So to me, the golden rule is that we need to develop cement, blended of course, with the least amount of advanced CO2, but that have sufficient performance to enable their use without significant increase of the binder content per cubic meter. And this, I think, is what distinguishes LC3 with other blended cements, that it allows me to translate the CO2 saving from the bag of cement to the cubic meter of concrete very efficiently. And this is what in this Altering Concrete project, we summarize in this concept as the twofold strategy, where we look at the CO2 of cement, which of course is related to the clinker factor, but more importantly, we look at the CO2 of concrete, which is related to a reduction of the base volume per cubic meter. And what is the potential of doing this? Why we are interested of shifting the focus out of cement and put the spotlight back to the construction material? I invite you to follow the equivalent CO2 footprint that is shown there on the right, that is normalized to a typical concrete of the Swiss market, 350 kilograms per cubic meter, cell 2A. So this is the benchmark that we are using, and we normalize that one to 100 to make it easier to compare. So that concrete will have a composition more or less like the pie chart that you see here. And with things that like LC3, we already go a long way because we can replace half of that cement with a combination of calcium clay and limestone, and we can reduce our CO2 footprint by about 30 to 40%, which is what we see here. I already showed you that in some markets and in some applications, it actually makes a lot of sense to think that we can go lower and we can reduce the clinker content even further. But we cannot go to zero. There is a higher price to pay in terms of efficiency of performance as low as we go in the clinker content. So there is definitely a reduction on amount of CO2 and clinker that is plateauing up to a certain point. So we cannot go infinitely down in the clinker concrete avenue. But if we move in the other direction, and we now look at reducing the amount of binder in the system, the amount of cement paste per cubic meter, is when we can really move and transition from a typical concrete with 100 units of CO2, if you want, to something that has virtually a quarter of the CO2 than the original mix. And this is why I think that the road from traditional concrete to the green concrete of the future that we need is paved with clay and limestone, because there is basically no other stuff available in that quantity, but also with high performance admixtures. And this is key, as I will illustrate in the next slide. And this is basically what I summarize as the workability challenge of low carbon concrete and ultra green concrete in particular. We are trying to reduce the clinker content. That basically means putting more SCMs. SCMs, if we want them to be reactive, they have to be high surface area. And this will have a negative effect in our workability. It's inevitable, it is what it is, and we need to deal with that. At the same time, I'm proposing that we should be reducing the binder amount, the amount of paste, and this basically means reducing the amount of lubrication between aggregates in the concrete mixture. And this also will have a negative effect in my slam and my workability. So there is a clear workability challenge here that we need to have addressed with a mixture technology. And particularly the two properties that I'm interested to keep in my material are flow and flow retention. And believe me that flow retention is probably the most challenging one, because it's where thixotropy and build-up of system containing calcite start to play a major role. And these are phenomena that definitely we do not understand completely yet. But this is what we have at mixture. This is PCE coming to the rescue. So PCE are these polymers that are in most advanced modern plasticizers and super plasticizers. They have a backbone that controls the absorption in the surface, and they have side chains that basically provide the steric hindrance and therefore the repulsion between particles. In this blended cements, the situation is though a little bit more complicated. So we have this lonely PCE molecule entering the world and interacting with this LC3 or low carbon cement, and basically we need to answer now a question of where this admixture is absorbing. We have much more surfaces than just the clinker, as in the case of OPC. Moreover, this process is dynamic, so there is a kinetic component that we need to consider in our equation. On top of that, there is a lot of admixtures, particularly from the family of PCE, that are known to hinder the hydration of elite or C3S. So there is a counterplay as well, as we were talking in the reducing the clinker factor, between keeping rheology, keeping flowability, open time and initial flow, versus hydration kinetics, and we need both. And there is certainly an optimum between the two, and what we need to achieve is basically develop new generation of admixtures for this cement that enable us to get flowability without sacrificing early age performance. It's important when we are talking about CO2 to review or to have a look at how CO2 and how environmental impact of this material is quantified. So a very classic way of doing this is to compute or to show the kilograms of CO2 per kilograms of cement that we are using. And there are numbers here that are very well known to you. For example, clinker 0.85, classic reference numbers, super plasticizer 1.88. But the problem of this indicator is that it's looking at the bag of cement, and as we said before, this is not a construction material. And what happens between the bag of cement and the truck of concrete is uncertain. And it's not always the case that the CO2 saving at this scale is effectively transferred to the concrete scale, because there is performance involved and there is mixture design involved. A more useful scale then would be to look at the kilograms of CO2 per cubic meter of material, looking at the concrete scale. And what we see here, which is also something that Karen already somehow introduced in her presentation, is that there is a lot of scattering. So for example, if we look at the Swiss average in 2019 was about 216 kilograms of CO2 per cubic meter. But if we look at a publication looking at the situation in the USA, in the Great Lakes area, this value is around 280 to 340. So around the world, we are producing concrete with a very varied amount of embodied CO2, and this is certainly a huge opportunity for optimization. A third scale, and the ideal probably would be to talk about CO2 per square meter of building. There is already some regulations like the RE 2020 in France that are looking at setting limits to the amount of CO2 per square meter of new building. The interesting things of this scale of quantifications is that each of them is talking to a different stakeholder of the value chain. The first one is clearly speaking to the cement producer, the second one to the concrete producer or the engineer, and the third one likely to the architect or the designer. It is very easy for me to expect that since the designer will be able to estimate what is the limit CO2 per square meter, he will be able to transfer that requirement to the concrete producer, and therefore the concrete producer will set a limit to the maximum CO2 per cubic meter that he can produce. So in my opinion, these are basically the two metrics that are more useful to move forward, and we need to start looking a way of quantifying this at the scale of cement because it neglects how the material is actually being used. And if we look then at the kilograms of CO2 per cubic meter and the decarbonization potential of the twofold strategy, this idea of reducing clinker and reducing binder, what I'm doing here is looking at a data set that was published recently of different concrete mixtures in different studies all over the world. So there is, you see a distribution of the amount of CO2 that these mixtures have, and basically, and this is obviously a proposal, and the numbers and the limits are open to discussion, and the more data we get, the better the proposal that we can do in this sense. We can establish kind of regions. Where are we trying to go with something like we could say low carbon concrete, or with something that we would call ultra green concrete? And what would be like the clinker factors and the binder content that would enable myself to get into those ranges. So we can see, for example, that if we take the average value, which at the moment in this data set is 250, and then we take the best 15%, we can set one limit for low carbon content, let's say 160 kilograms per cubic meter. And this is basically a range that we can easily access with LC3. So if we all use LC350, we can basically produce already low carbon concrete out of the box with any almost binder content that you want. This is assuming a worst case scenario for clinker, so if you improve your clinker as well, that opens the gate. But the ultra-green concrete project is a little bit more ambitious, and we propose to go and to develop technologies to enable making concrete with less than 100 kilograms of CO2 per cubic meter. The problem with the previous approach is that it neglects performance. It doesn't look at strength, so probably it makes more sense to look at the data on a way similar as the group of Professor Van der Leyen did in the ultra-green concrete eco-efficient cement report for UNED, where we normalize this CO2 intensity by megapascal, and we can establish the same kind of limit. So the green area would be low carbon concrete, limited by these values here, and ultra-green concrete would be lower than 100 and then stay stable at a certain value of CO2 cubic meter megapascal to not penalize high performance material. It looks very challenging because if you see there are not so many points in the ultra-green concrete area. This is basically because how the codes are made now in Europe. But based on the trials that we have been able to make so far in the lab, you can see that it is very much possible to get within the low carbon concrete section of the plot, and in some cases we have been able to incur in the ultra-green concrete without still optimizing that mixture. So there is a lot of potential and a lot of hope that we will be able to achieve this during the duration of this project. And these are some of the mixtures that we have been working to. So the first two, based on this arbitrary definition that I proposed, would be low carbon concrete. The last one would be an ultra-green concrete. You see the strength there, the binder contrast, and these were all made with LC350. So we're not even going yet into the direction of reducing the clinker factor even lower. The problem with all of these technologies is that the EN standard for concrete has a prescriptive approach to meet the durability requirements, which is basically a deemed to satisfy idea. There is a certain water to cement ratio, there is a certain minimum binder content that someone, based on experience, established that is required to meet a certain criteria of durability performance. And the problem is that these kind of prescriptive tables do not enable us and allow us to move into low carbon concrete materials. So I think that since changing standards is something that takes time, definitely we need to do it. At least we should allow, at the minute, alternative verification through performance testing. So allow people to do low carbon concrete and validate their exposure and durability performance through testing. And the interesting part of that is that probably the outcome of this testing can feedback the standard, and we can enter into a more extended discussion of how we change the standard into a performance-based qualification for durability requirements of concrete. So with this, I would like to conclude my presentation with the main ideas that I have presented. So the first, we can only move forward with cement-based materials on a worldwide scale. There is just nothing else available in the scale to make a significant replacement of cement-based material, particularly concrete. Using calcined clays and limestone enable enormous cuts in clinker, not only because they are available, but also because they are reactive. And that reactivity is really what opens this whole new avenue of exploring systems with 20% clinker, 30% clinker, particularly in cases where PC level strength is not required. Chemical admixtures, in my opinion, are the enablers of sustainable concrete. Without chemical admixtures, we're not going to go anywhere because we have a workability issue at hand that we need to solve and tackle if we want to achieve things like low carbon concrete and altering concrete. And we need ambitious, like these two limits that I put, I offer as a proposal here in my presentation, but still attainable, like the LCC range, goals towards decarbonization of cement and concrete industry. And I think that we need performance-based metrics to move forward, because this is the only way that we are going to move from comparing bags of cement to comparing materials in field applications, and therefore apples with apples and not things that are completely different. I would like to thank everyone for your attention, and more than happy to take questions during the coffee breaks or during the conference if we cross in Colombia.